You're deep into a step 2 block, and suddenly you hit a wall of text. P-values, confidence intervals, Kaplan-Meier curves, and shifting denominators. Step 2CK emphasizes clinical logic and pattern recognition over the derivation of complex math. To navigate these questions consistently, you need the diagnostic algorithm, a mental framework that breaks down any vignette by interrogating the study's architecture rather than memorizing isolated definitions. Auditing a study's timeline and denominators allows you to bypass distractors and arrive at the intended statistical measure. This flowchart is the baseline for every biostatistics question. Your first question is, how were participants selected? If researchers select patients by their disease outcome and look backward for a history of exposure, it is a case control study, yielding an odds ratio. This NBME explanation confirms the logic. Case control studies group patients by outcome status to analyze the odds of exposure. Since the exposure wasn't tracked in real time, the study cannot establish causality. Selecting patients by exposure and tracking them forward defines a cohort study, allowing measurement of incidence and relative risk. Measuring both simultaneously defines a cross-sectional study, providing disease prevalence. Randomly assigning an intervention is a randomized controlled trial, yielding absolute risk reduction and the number needed to treat. Analyzing entire populations is an ecologic study. Pooling prior trials is a meta-analysis. Identifying this chronological axis eliminates mathematically impossible answer choices before you even look at the data. In biostatistics, the vast majority of calculation errors stem from a single source, misidentifying the denominator. Prevalence versus incidence reveals this. Incidence's denominator only includes the at-risk population, excluding existing cases. Similarly, mortality uses the entire population as the denominator, while case fatality only counts those who already have the disease. Attack rate uses exposed individuals as the denominator, while secondary attack rate narrows to only contacts of primary cases. Attributable risk measures excess risk within an exposed group, but population attributable risk measures impact on the entire public. Focusing on the denominator prevents you from being misled by numerators designed to mirror each other. Randomization is used in trials to balance unmeasured confounders that researchers cannot identify at the start of a study. To protect this balance, allocation concealment prevents selection bias before the trial, while blinding prevents observer bias during the trial. Validity issues arise when patients drop out or cross over. Intention to treat analyzes every patient in their original assigned group, preserving randomization. Per-protocol analysis only includes compliant patients, measuring biological efficacy but ignoring real-world non-adherence. Intention to treat provides a more realistic measure of a drug's effectiveness in a population where patients are often imperfect. The 2x2 table organizes disease status in columns and test results in rows. Sensitivity and specificity are calculated vertically down the disease columns. Predictive values, representing clinical reality, are found horizontally across the test rows. Predictive values shift based on a population's prevalence. In a low-risk population, the false positives easily exceed the true positives, causing the positive predictive value to drop significantly, even if the test is highly specific. In clinical vignettes, you will see highly sensitive tests used on asymptomatic patients with no risk factors. Because false positives outnumber true cases in this scenario, the correct management is often reassurance or routine follow-up, rather than an invasive confirmatory biopsy. Bias is a systemic error in data collection, such as recall bias in case control studies, or the Hawthorne effect, where behavior changes due to observation. Confounding occurs when a third variable distorts the relationship between exposure and outcome. Stratifying the data will make the association disappear. Effect modification occurs when the exposure effect truly differs across subgroups, such as a drug working in men but not in women. Lead time bias is a distortion of survival data, common in screening studies. Earlier diagnosis makes the survival time look longer, even if the actual death date is not delayed. Additionally, length time bias occurs because screening preferentially detects slow-growing, less aggressive disease, missing fast-growing tumors that kill between screening intervals. Identifying more disease earlier is not the same as saving lives, which is why absolute mortality is the primary metric used to validate screening programs. To finish, Let's review all the essential reflexes and mental frameworks you need for biostatistics on the exam. If grouped by disease, look for an odds ratio. If followed over time by exposure, look for relative risk. If measured at a single snapshot, it's cross-sectional. If the denominator is the population at large, it's mortality. If it's only the diseased, it's case fatality. If survival appears to lengthen but the death date is unchanged, it is lead time bias. If screening overrepresents slow-growing tumors, it is length time bias. Multiple subgroup analyses increase the risk of a type 1 error. Small studies with wide confidence intervals that show no difference are likely suffering from low power and a type 2 error. Step 2 CK Biostatistics is a predictable exercise in logic. Interrogate the denominator, audit the timeline, and trust the algorithm.